2. Center of gravity. It is the single point of an object where its weight seems to act. To balance a body in equilibrium, the weight and the normal reaction must pass along the same line as shown in Figure 5.2c. The center of gravity, Cg, of a symmetric body is at its very center, the midpoint of a ruler, or the center of a circular disk, and so on. For irregular objects, we may find its center of gravity quickly by experiment.
Here is a cardboard of irregular shape. We will locate its center of gravity. Loosely hang the cardboard at a point near its edge on a notice board with a drawing pin. The cardboard should be able to swing freely. Suspend a piece of string with a nut on the drawing pin. Mark the position of the string on the cardboard. Now suspend the cardboard at another point near the edge. Then suspend the string too. Mark the position of the string on the cardboard. The intersection of the two lines is the center of gravity of the cardboard.
The position of center of gravity of an object affects its stability. In Figure 5.2d, the chair on the left is stable as the weight at between the base of support of the chair. In the second picture, the weight produces an anti-clockwise moment about the pivot O, which is called a restoring moment, that restores the chair to equilibrium. In the third picture, the clockwise moment produced by the weight about pivot O will further turn the chair over. Example 5. Supporting point and CG. The stunt rider appears to be pretty dangerous, but by physics, we know that they are pretty safe. The weight of the man in red produces a clockwise moment about the wire that brings the bicycle away from vertical, but the weight of the man in blue produces a restoring moment that brings the inclined bicycle back to vertical. The restoring moment is made larger by a heavier stunt man at the bottom and the length of the hanging swing. On the other hand, we may also look at the combined weight, which produces a restoring moment for the whole object to bring it back to the equilibrium position, as the center of gravity is under the point of support. Example 6. Forces acting on a ladder. A difficult question from the first glance, and even more difficult if the wall is not smooth. We know immediately that the reaction by the wall is normal to the wall. First, we draw all the forces acting on the ladder. In part B, the reaction R by the ground is the resultant of its friction and normal reaction. The normal reaction by the floor is easily found, but what about the friction? Same as the normal reaction by the wall. But how big? As the ladder is in equilibrium, the net moment about any point, say the point Y, must be 0, and so the normal reaction at X is found. You may also try to find the net moment about point X instead, which gives friction F equals 27.4 Newton The same as when you take moment about Y to find the normal reaction by the wall. Read the solution carefully. Example 7. Trunk in equilibrium. This is a common question type. Read the solution carefully. Many open exam questions are similar to this question. Now, try checkpoint 4 below.